Hello everybody, welcome to my channel. Today we will be discussing about special case of species A which is diffusing through B. So species A is diffusing through stagnant B. So B is here non-diffusing. Here there are two examples. That is example if we take, this is an example number 1 and this is example number 2. So example number 1 says that ammonia in air is being absorbed into water. So there is air is flowing above liquid water. It is having some ammonia in it. So ammonia is getting absorbed in water. Here you see, if you note that species A, only ammonia from air is being absorbed into water, not air. It's being absorbed here. So air is having a negligible diffusion here. So we can say that A is diffusing, that is our ammonia is diffusing through non-diffusing B. Further, another example is there in this test tube. In this test tube, we are having diffusion of A to stagnant non-diffusing B. So here benzene is evaporating. So benzene is what? Benzene is evaporating into bulk here. So what is here? This is actually, so if you can take, so liquid benzene in a nanotube is occurring, and at time t level, a certain time t, the level of benzene in the test tube is 0. After a certain time, suppose that after a certain time or at the final time period, the level drops after evaporation of liquid benzene to certain level, that is ZF. This is somewhere over here. So initially, liquid in this liquid benzene in the test tube was at the level of Z0. Finally, it is at the level of ZF. So if this is the case where liquid benzene is evaporating into bulk here, so A is diffusing into non-diffusing of stagnant B. In these cases, the case of diffusion of A to stagnant or non-diffusing B at steady state often occurs. In this case, one boundary at the end of the diffusion path is impermeable to components, so it cannot pass through. So one example, two examples as we see here. Another example can also be seen. So at point 2, we can say that partial pressure of PA2 is equal to 0. So partial pressure of 2 here is certainly 0 here. So there is a certain gradient. So it has partial pressure PA1 some value here, some certain value is there. PA2 here is 0. So diffusion of A is occurring. Since the large volume of A is passing by. So the water surface is impermeable to air since air is only very slightly soluble. So we cannot diffuse into B. So our flux in B, diffusion flux in B here is 0. In these cases, to derive the case for A diffusing to stagnant non-diffusing B, that is NB equal to 0, or in B, that is PA1 a certain value and PA2 here is having certain value. So partial pressure is, there is a partial pressure gradient here. In these cases, how do we derive or obtain an equation? Derive for the condition of A, we are having, so we write for case for A diffusing through non-diffusing B, that is NB is our 0. So in my earlier video we saw that for flux A, convection plus diffusion, we can write N is equal to minus CdAB dxa by dz plus A by C Na plus Nb. So since it says that B is stagnant, so we can write B is non-diffusing, B is 0. So see, it becomes Na plus 0. Now this equation, if we further solve, we find that the convective flux of A can be written as Ca by C Na plus 0. This term, that is this term. On if we keep the total pressure P is constant, substitute of ideal gas, we will find that C is equal to P by RT. Now Ca by C can be written as Pa partial pressure of A by total pressure. Concentration of A by total concentration is written from the ideal gas law, the partial pressure of A by total pressure. Further, we can, if we replace these terms in this equation number 1, we get Na is equal to minus of Vab by RT dPA by dz plus A by P Na. Now on rearranging and integrating, we find that Na can be written as Na is 1 minus Pa by P is equal to minus of dAb by RT dPa by dZ. Na can be written as Z1 from Z1 to Z2, distance which has been traveled, and in dZ is equal to minus of dAb by RT dPa by dZ. Again on solving, Na is equal to dAb. This is our total pressure. We can write it as PT RT Z2 minus Z1 ln of, to solve this integration to dPa by dZ. We will solve from PA1 to PA2. So PT or total pressure can be written as PA1 plus PB1, it can be written, or it can be written as PA2 plus PB2. Things like that. Now, if we solve this integration, we find ln is equal to P minus PA2, or if it is the PT can be written as PA1 plus PA2, like that. So, since we have been asked about A only, we can have P minus PA2 divided by ln of P minus PA1. So when we final equation is solved, we have to calculate the flux of phase. Since it's overwritten, P can be written as, we can write P as we told earlier, that P is PA1 plus PB1 here, or PA2, this should be not there, PA2 plus PB2. So now, like this, we can write PB1 is equal to P minus PA1 and PB2 is equal to P minus PA2. Now, we solve that log mean pressure difference, that is PBM to PB2 minus PB1 by ln of PB2 divided by PB1. Similarly, for A, we can write PA1 minus PA2 divided by ln of P minus PA2 divided by P minus PA1. Therefore, on substituting this equation, all these values in this equation, that is equation number 2, right? What we get, Na is equal to dAb P RT delta Z, Z2 minus Z2 delta Z, PBM PA1 minus PA2. So this is the equation for A diffusing through non-diffusing B. A is diffusing in stagnant non-diffusing B. Thank you very much. In my next video, we will be discussing certain examples of diffusion of water to stagnant non-diffusing air and a tube which having certain partners. Thanks for watching. Please do subscribe my channel.